is made of briquettes. This wall separates the hot air inside the furnace from the outside environment. The wall thickness is 0.25 meter and the heat transfer coefficient of the briquette is 1.2 watt over meter Kelvin. At steady state, the external surface temperature of the wall is 120 Celsius degree and the surrounding temperature is 25 Celsius degree. The heat transfer coefficient between the wall and the surroundings is 20 watt over meter square Kelvin, and the radiation emissivity of the wall is 0.8. Find the internal surface of the wall. First of all, let's write the values given to us. The wall thickness is 0.25 meter. And the heat transfer coefficient of the briquette is 1.2. Okay. The external surface of the temperature is 120 Celsius degree. So T surroundings is, the surface (120 Celsius degree) and the surrounding temperature is 25 Celsius degree. And the heat transfer coefficient between the wall and the surroundings is 20 watts over meter square Kelvin. And the emissivity is 0.8. Here, there are three heat transfer mechanisms in this problem. What were the heat transfer mechanisms? Conduction, convection, and radiation. The problem asks us for the temperature inside. By the way, if I think about the shape of all furnace wall, for example, like this, and the briquette is here, this is surface temperature and this is internal temperature, right? Since the external surface of the wall and the surrounding temperature are different from each other, we can say that there is radiation heat transfer here. I also have convection coefficient between the wall and the surroundings. In other words, there is also convection heat transfer. Can I think like this? Considering the energy coming from both surroundings and the surface temperature, needs conduction to change temperature on the inner surface. This is so important to understand here. Please note this. So let's write the equation on the surface furnace. Okay. If you remember, I have Q convection here and Q radiation, and they are equals to Q conduction. What was the Q convection? T2 minus T surroundings plus Q radiation epsilon Stephen-Boltzmann constant T2 power 4 minus T surroundings power 4, and they are equals to Q times T1 minus T2 over L. So, so let's substitute the values here.